Thank you.
So nice to like take a breath. Did you?
Yeah. We had a away game, so we're just gonna go on the weekend.
What did you see soccer?
Last week in February.
Oh, because you just started.
Yeah,
Hockey,
just
right?
yeah. We have such a long season. It's so long. We started skating like 4 weeks ago. Like that's literally the entire year.
Props to you, man.
I don't know if we're gonna make it.
Okay, so we're making confidence intervals for different parameters. So today we'll look at the bootstrap T method of making confidence intervals. The homework 7 is posted. There's a few problems that do things on proportions, and a few things that do these bootstrap T intervals. The first problem, 7.24, asks you to do confidence interval proportions just using the simple formula. You can basically do that by hand, p hat, 1 minus p hat over n, standard error. So you do that, there's 2 groups, and there's a difference. Right? And then it asks you to redo it with the more complicated formula, right? The Wilson adjusted one that is in the book, that's a little more. That one's also encoded in the proportion test commands. So you could do the computing just from numbers. You need the number of successes or occurrences out of the 2 groups and the 2 sample sizes put in there in that formula, and we'll give you the results. Right? You don't necessarily have to go through that big formula and put it in there, but I suggest you read it and think about could you fill it in if you needed to. Primarily, we would use the simpler form for on an exam or something, because again, that's a lot to remember, right? And then a couple data set based problems for this T in there, and a few things have been added. These are the data sets, and they've all been read into this R data file, so you can just upload that. That would have things in a little bit of script. And the script doesn't give you all the code for doing the bootstrap, but it kind of sets it up so you have the data loaded. Right? And there's an example in the book that does the bootstrap type of things that we're doing. And you would do that, but need to modify it just for the new variable name. Right? So at one point it says, alkalinity or chlorine or a different variable name, and you just kind of modify the code a little bit, but follow the general pattern. Right? So it gives by doing that, I think you'll get a little bit more of the experience of doing the coding, but it's not where you have to do a lot of completely different things. So maybe it's good practice, a good way to see how it runs and to work through it. So that's all posted. It's due Friday, so if you work on it over the next couple days, office hours, Wednesday, Thursday in particular, would be a good time to ask about that stuff. So we should be able to cover everything we need today for that homework on Friday. So those parts of it like that. But any questions about the class or schedule? Right. So bootstrap intervals, the general problem is always good to keep in mind is that we have a population we want to know something about. We want to know its characteristics, which are going to be encoded in parameters. Some parameter theta, and then we're going to get our data, and we're going to have an estimator, theta hat. Could be simple, could be complex, and so on. And we want to do inference back up here, and the form that our inference is going to take is going to be a confidence interval. For our parameter theta. And for some parameters, we've seen a few ways of doing confidence intervals, and today we're going to see a new one using the bootstrap to mimic the T distribution. So it's a little bit different, but in some simulations seems to work out well, right? So that's the general, the kind of big picture perspective of what we're trying to do. And so we've seen some ways to do, so we have a parameter theta, and we have an estimator. And one way we did this back in chapter 5.3 is we looked at bootstrap percentiles, which is one way to get an interval, right? And so we recall what we did with that one. We had data, x1 up to xn, right? We bootstrapped it, take a sample size in with replacement, calculate a new theta hat. Do that 10,000 times, and take the cutoff points that isolate the central 95%, and just call that an interval, right? So that's still valid. That's something that could be done. So generate, right, a bootstrap sample. So to do that, we sample n times from our data, x1, x2, up to xn with replacement. So you can have a little bit of variability in there and compute theta hat, say b for that bootstrap sample, right? As a function of our new data, right? And do this, many times, say 10,000 is what we'll do in simulations today, right? And then simply report the, sort all the values, report the, which one is that going to be? The 250th theta hat, the 250th up to the theta hat 9,750, right? In that order, and report that as an interval. Right? And if the sample size n is not too small, right, the bootstrap samples can have a lot of variability, and take enough bootstrap samples so you can kind of determine those endpoints pretty well. So it should work pretty well in many cases. Right? Another way to use this bootstrap sample would be to just estimate the standard error and then mimic what we do with the t-distribution. Right? So a second one would be to use bootstrap standard error and essentially report theta hat plus or minus a t-value. Our book gives the notation alpha over 2 for n minus 1 times standard error. And mostly this is thinking about a mean, right? Kind of mimics what we do for a mean. And the standard error is from that same bootstrap sample. So the variability of this thing, this theta hat of these minus the kind of the average of the theta hats, that thing squared, divide by capital B minus 1, and I take the square root of all that. So the variability of our theta hats, those are like simulating the sampling distribution, and if we simply have a standard deviation of those, that's like our standard error. And for x, we use this t-distribution instead of normal. So instead of using 1.96, we're going to use 2.02 or something a little bit bigger to reflect our finite sample size. So that'll be a different interval that we might use. Seems like a reasonable idea. How are these different? Obviously, they're slightly different procedures, but what is an implication of this procedure? One of them is symmetric. Right? This one is guaranteed to be symmetric. You go to an equal distance below, equal distance above the estimate, and so you get, this one is a symmetric interval. And it very well could be pretty close to the t-interval, right? The ordinary t-interval where we use s over the square root of n. A virtue of this one, You don't necessarily have to use X bar. You might be able to use something different. You might think about whether you want to use a t-distribution there. That's a different question. This one's symmetric. This percentile one, right, is not necessarily symmetric. This one can be asymmetric. Right? If the simulation gives you a distribution that has a heavy tail in one direction, right, then the interval is not going to be symmetrically centered or equal distance from theta hat. Right? That reflects the sampling distribution. That could be a good thing. Right? So if the distribution is really skewed, these two things are really kind of different. But if the distribution is not so skewed and the sample size is big, they're probably pretty similar. Right? We're going to introduce a third option here, which is going to be called the bootstrap t-interval for a mean. That's supposed to be a t. Right. And so in our bootstrap samples, well, in a t-interval, right, we had to use that t-value. Right? The t-interval is symmetric and has a certain shape and certain skewness, certain kurtosis, right? A certain heaviness of the tails, right? So that's a specific distribution. But with bootstrap, we can actually simulate something like a t-distribution, right? So in the real problem that we're facing, we want to know mu, and we calculate X bar, and the t-distribution, the standardized statistic, the pivot, is X bar minus mu s over the square root of n, right? And then we compared that in the t-interval to a t-distribution in minus 1. Right? In our bootstrap world, right, the bootstraps generally are centered around X bar, right, because we're sampling from that set of data whose average is X bar. Right? And then for our new bootstrap sample, we get an X bar star, right, a new simulated average. And so we are going to form T stars. There's X bar star minus our X bar, the standard deviation of this bootstrap sample over the square root of n. So that's like a bootstrap sample from the T distribution, or whatever that distribution ends up being. Meaning it can be asymmetric. It doesn't have to be symmetric or like T. It could be skewed. Right? And so we're going to get, thousands of 10,000 of these. Right? And then we are going to find the 2.5th and the 97.5th percentiles of the T star. Right? And let's call these things the T star 0.025 and the T star 0.975. Right? So as you make a plot of these things, and it's not exactly normal, we're going to find the two values out of the 10,000 that give us kind of the 2.5% tails. Right? So then we're going to make an interval that looks like a t-interval, times the s over the square root of n from our original data, but use these t stars instead of the t from the theoretical distribution. Right? So let's go back to this color. So our 95% confidence interval for mu is going to look like the X bar minus a t value, a t star value, times s over the square root of n. Right? And then X bar plus, no, it's still minus. We'll go through this logic why it's minus s over the square root of n. And the one we're subtracting up here is the small one, which is generally negative. And this one we're subtracting down here is the 975 value, which is generally positive. And that's going to end up being our interval. And this is the S from the original data and X bar from the original data. So it kind of looks like a t interval, X bar plus or minus t times the standard deviation. But these things are not necessarily the inverse of each other, because it might be asymmetric, because we're bootstrapping, right? One thing we can add to this picture is 0 is probably pretty much in the middle, here somewhere. It might not be exactly in the middle, because there might be a little bit of skewness, but usually it's pretty close there, right? So that would be our other interval. Right? Another way of giving it. So why do we minus those two things on there? Well, it's the same logic that went into the pivot. That when we undo the pivot thing, we ended up with a minus there. And so let's see how that goes. Oops. Right, so that's our interval. Right, but any questions about what these symbols are? Yeah.
So 95% of the t star values are in this interval?
So these 2 points are calculated by 95% of the t star values. Right? When we did the ordinary t interval, x bar plus or minus the t 0.975 s over square root of n, right? This is kind of the ordinary t interval. Right? These things came from a t distribution with n minus 1 degrees of freedom. So under that theoretical distribution, let's try to draw a little smoother, right? We would take the 95% interval in there. Right? And so this upper cutoff is the mirror of that one, so we can write it just as plus or minus. Right?
But the t stars are not necessarily symmetric.
Right, but these are the simulated values, and we end up taking those in its place. So, the, right, so if the t star, like the 0.025 value, like this lower value, right, should be less than or equal to our x bar minus mu, right? If that's true, right, we're going to simulate a bunch of t stars and take the cutoff values and think of those bounding this relationship in there, right? Instead of using the theoretical distribution values, we use these simulated values, replacing theory by simulation. Right? And so if you take this left hand over here, you can multiply, we can make 0.25. If we multiply by s over the square root of n, that's less equal to x bar minus mu, less than or equal to the 0.975 star, right, s over the square root of n here. And now, if we take just the one side part of it, we just take this part, we can add mu to both sides and subtract this part. Right? So we can get mu on this side is less than or equal to x bar minus, because now we're going to minus this over here, 0.25 star, right, s over the square root of n. So that's our upper inner point, right? Remember the t 0.025 is probably a negative value, like -2, something around that range. And if we also take this half, right, this part of the equation in there, we can add mu to both sides, so mu is going to be over here. And again, we're going to subtract this from both sides of this equation, so we get x bar minus the 0.9, the t 975 star, and this s over the square root of n. So we take the big value, about 2, and we subtract it, and it's down on that side. And that's the other form of this interval, right? And that's it. That's the t interval, right, for this. And it gets a little more complicated when we want to do the difference of two means, because we need to do a couple. Yes?
So it means this interval is equal to mu?
Is less than or equal to mu. Right, so mu is, this is the lower part and this is the upper part. Right? And so mu should be between those two. We're 95% confident that that interval, that mu is in that interval. Right? So anyway, I'm showing you here that this is the lower part, this is the upper part, and so the interval that we had, right, that's where we get the minus these two things, right? From undoing those equations. It's connected to the pivot, right? Because with the t, the ordinary t interval, we had something that if the distribution is right, it really is that t distribution, and we unsorted it that way. Right? But just a slight variation. So let's look at a numerical example, see what it looks like. Then we can talk about it. This is a good idea. So problem 7.220 deals with this ice cream data set. There are a number of brands of ice cream, and calories, fat, sugar, etc. from vanilla and from chocolate. Right? No chunky monkey or anything like that, just kind of strawberries or whatever your favorite might be. Right? So those are the first several rows. Anyway, I just called it IC for short to make it easier to deal with. And so I'll run that to attach those things. And here's a plot of calories of vanilla versus chocolate, right? And this is a slope 1 line, right, where they're equal. Right? So for some brands, chocolate is more, sometimes chocolate is less, right? Doing it this way, vanilla is more, vanilla is less, right? So, but it's not too different in there. The average of vanilla is 191. The average of chocolate is 198, almost 199. So chocolate's a little more. So our estimate of the difference could be the estimate of those differences there. And so we want to ask the question: is this significantly different from 0? If we make a 95% confidence interval, is it going to include 0, no difference? Or is it all going to be positive? Well, it's going to be negative if we've done it this way, vanilla minus chocolate, because the chocolate was bigger, right? This is a matched pairs because each chocolate and vanilla was done under the same brand, right? So we really want to take differences and treat it as one sample of differences. They're not two independent samples because of the same brand. And so to do that, I'll take differences. This works because I had attached that variable, so I can just refer to the column names in there. If ever you're running something and it says you can't find vanilla or can't find chocolate, don't be sad. You just have to attach it. And I imagine, telling a kid that there's not any ice cream of a certain type. Oh well, it's there. You just got to make sure it's attached. So the differences. Here are the differences. A vertical line at 0. There's the 0 line, as you could tell. So more of the differences are negative. There seems to be a couple that are pretty big differences. Oh well, we'll just kind of go with that. So if we do an ordinary t-test, right, it runs and we get these results. Right? There were 39 different brands, right? The average difference, taking vanilla minus chocolate, was the negative 7.3, which means that chocolate was more. And here's our 95% confidence interval based on a t distribution. When we do hypothesis testing, which we'll revisit the p-value if that's small, it's significant. Right? We would not expect to get a value of negative 7 given these sample sizes and so on. What are the components that go into that? This is the standard error, the standard deviation of the differences. What is this by itself? The standard deviation of the difference is about 12.9, almost 13. Right. So here, kind of the middle, plus or minus a couple standard deviations, is the individual differences between brands. But for x bar, we divide by the square root of 39. So we get a standard error of 2.07. The t-value we would use is the 2.02. So if you take the negative 7.33 plus or minus, and this is a little tricky way to get that done, 2.0244 times 2.0707, we get something like our interval. Well, it's not quite the same. Did I? 707.2. Oh, right. 02. That's it. Right. Then that's about the same as the one that's up there. So that's our ordinary t interval. Right? Most people would report that, right? But we could try for bootstrap, right? It's this distribution of differences. It's a little skewed. It's not too terrible. 39 is not that small. So I wouldn't be too unhappy with this one. The bootstrap sample, we have to set up some code. Right? We are going to do 2,000 bootstraps. The bootstrap average, I'm going to call D bar, kind of the average difference. Right? Set a number seed so I could redo it if I wanted to. Then I go through a loop. I take a sample of size 39 with replacement and record the mean. Right? So that's the whole bootstrap thing. And I run through that. And here are the bootstrap averages. Right? -7 is pretty much in the middle. Right? 7.3. So pretty much there. The 95% quantiles for that is a -11.49 up to -3.54. And that would be this interval for where the average is. This one's a little bit narrower, more narrow than the t-interval. One thing that the book says in terms of evaluating things is it says that this percentile one often makes intervals that are a little narrower. There's probably a deeper theoretical reason that it's doing that. It's doing something like mimicking dividing by n in the standard error rather than dividing by n-1, so therefore it's a little narrower. But you could probably adjust that a little bit. If you look at those 95% intervals on the graph, there's 7.33. And those are the bootstrap percentiles. Right? So you could check, is it symmetric? The distance, what this is doing is taking the difference from the average, right, the average difference, -7.33, to those two quantiles. The distance from here to here and from here to here, and then taking the absolute value, so it's all positive. And it looks like the distance on the lower side, right, is a little bit bigger than the distance on the upper side. So it's a little bit asymmetric. There's a little bit of asymmetry in the plot of the data, and so in the averages, it's sampling distribution. It's a little bit asymmetric. Right? So that would be that one. You could also just do the bootstrap t-interval, but use the standard error for the bootstrap. Right? That's pretty simple to do. You do the mean minus the standard deviation, or the t-value times the standard deviation of the bootstrap values. Right, the standard deviation of the bootstrap values is 2.04. What was it? S over the square root of n is pretty similar to that. Right? So if you do the standard deviation of the differences divided by the square root of 39, that was just a little bit bigger. Not too much different. Right? But if you do the standard deviation of the bootstrap values, you get an interval here. It's a little narrower than the t-interval from before. It is symmetric. So it's kind of like the t-interval, but a little bit narrower. The book kind of emphasizes that standard error kind of underestimates a little bit sometimes. Right? So it's maybe not the best choice. Since the t is symmetric, we can do plus or minus the 0.975, or we can do minus the 0.975 and minus the 0.025. Right? So there's kind of two ways of doing that. Mostly people say plus or minus the positive value, but if you subtracted the positive or subtracted the negative, you're going to get the two values that are there. So now the new thing, right? The bootstrap t-interval. So we're going to do a different bootstrap because we're going to keep track of something different. Right? So we're going to do 10,000 bootstraps. For convenience, I'm going to record the length of n so I don't have to retype that down there. Now I'm going to call these the bootstrap of the t values, boot.t. Set a number seed in case I want to repeat that. I'm going to sample the differences, so I get my bootstrap sample the same way. The thing I record is like a t-value. Right? My new average minus my average of my data, divided by the standard deviation from my sample over the square root of n. Right? So this is t. This is what we'd call t star in the symbols. An x bar star, S star, right? And so that's the type of thing that has a t distribution. Do that 10,000 times, and I can look at the distribution. What does it look like? Let's run it here. Run. That's what it looks like. Does it look symmetric? A little skew, right? So the quantiles are -1.82 and 2.29. The t-values when we did plus or minus, we're 2.04 or negative 2.04, right? So it's a little bit shifted to reflect that asymmetry. So this is where they are on that plot. 0 for our t-values in the middle. And so our interval is the mean minus those two quantiles times the standard deviation of our data over square root of n. Right? And we reverse these percentiles to get the bigger one first. So you're subtracting a positive value. And the second one is subtracting a negative value, so it becomes positive. So anyway, these are the intervals is that, right? So this seems a little bit shifted relative to the others. It goes a little bit below 12, whereas the other ones didn't. Right? So it's a little bit different, but pretty close. I mean, it's not drastically different. But it makes it reflects the sampling distribution asymmetry. It's kind of based on this idea of a pivot, but reflects the fact that we have a certain pattern in our data, and it kind of mimics. It has something that comes out of that. But that's it. Right? So if you wanted to do sugar or fat, you always have to do is change diff, or the difference between those two variables, vanilla calories, vanilla fat versus chocolate fat, and that would be your new diff, and then all the rest of the code would run through. Right? But anyway, you could see what that looks like. The second one has to deal with birth weights of children in Texas and weights of smokers and non-smokers. Maybe before doing that, we can talk briefly about how do these evaluate it. There's a figure in the book. I didn't copy it for you. Oops. I think I scanned it upside down. Rotate, that's reload. Is that going to turn it? No, it's reload.
Oh, right there.
This thing up here?
There's a bar.
There's a bar that comes up?
Yeah.
Yeah, there you go. Just hit the rotate button next to the bar.
Okay. There it is. And then we'll make it a little bigger, right? So there's some discussion of how do these confidence intervals perform, right? It's a little bit complex picture, right? But the idea of our confidence intervals is we want them to be accurate. We want them to cover. And sometimes they miss because the interval is too high, and sometimes they miss because the interval is too low, right? But we want intervals that are about 2.5% on each side. We don't want to miss all on one side or all on the other side. And so this thing, here's 2.5%. This is the one-sided non-coverage. What percent of the time do you miss on one side versus the other? And this must be for an exponential population is pretty skewed, right? So it's pretty skewed to one side. And they tend to miss above 2.5% on one of the sides versus the other. So the actual non-coverage, I think, is shown as a function of n. T is the lower t is the ordinary one. B is a t interval with a bootstrap standard error. P is a bootstrap percentile, and capital T is the bootstrap t interval that we've been talking about. There's two curves. The top curves show how often the interval misses by being too low. So the top curve, it's too low more than 2.5% of the time. So it misses up quite a bit. And the
Bottom curve.
T intervals, the P percentile intervals, and the bootstrap ones, they're all kind of quite similar in terms of how they miss. But this bootstrap T interval that we just did is a little bit closer to 2.5%. Right? Now, often if they miss too high, miss in one direction, they miss less in the other direction. Because if all shifted in the wrong direction a little bit, it kind of affects a lot of them. So when it's very high missing up here, it's closer to 0 here. When this gradually climbs, the T is the narrowest, closest to our 2.5% idea on too high or too low. Whereas the other ones are really missing on one side more often than the other. But then as the sample size gets bigger, this is not just a linear, it's like more of a logarithmic scale, that they come closer, whatever the skewness, to being close to 2.5% on each side. But the bootstrap T does better. Right? So the rationale for thinking about doing that is it would seem to, in cases where there's great skewness and the assumptions, central limit theorem's assumptions that the sampling distributions normal are less likely to hold, the bootstrap T interval would seem to have some virtues, right? So anyway, that graph and that discussion is trying to make the point that it seems to perform well in some more extreme simulations. And in cases where we have big sample sizes and things are not so skewed, we're less concerned. It's probably going to make much less of a difference. But in extreme situations, this seems to be a little bit better. Right? So that's what that confusing kind of involved graph does. Right? It also emphasizes what do we hope these things do. We hope to have 99% coverage. We hope to have it not be also lopsided, because that would seem to be not so good. So I wanted to look at one example with two groups. Right? So there's birth weights of smokers versus non-smokers, and we'll go through and do some of these different intervals at these different times. So there are smokers and non-smokers. There's a big difference. Right? These mothers, only 9 years smoking, and 1497 are not. Right? Here's a box plot of the weights of the children. Right? These are in grams. Right? So this is 3 kilograms, so about 6.6 pounds, something like that. Right? Near kind of an average. These are 9.5, 10 pounds. These are large. These are only 1,000 is pretty small. Right? 1,500 would be about 3 pounds. So those might be premature or something like that. And this is the two distributions. There's a lot more data points in here versus this. Some in both could identify as potential outliers, potential extremes. Right? And these lines are out of the median. So it looks like there's a little median shift in there. It's a little bit lower. Right? And the question is that statistically significant? The mean in the two groups is 3287 grams among the non-smokers, so that's the group that's higher, and 3205 among the non-smokers. So there's a difference of about 82 grams, 82.5 grams. Might not seem like much, but that at what point does it start impacting a baby's health to be lower birth weight? I don't know. So one thing you could do is save off the two groups, the weights for those, for the smokers and non-smokers. In R, it is case sensitive, so these were capitals in the original data set, and I made mine lowercase. Didn't have a particular reason for that, but I just did. Right? So the t-test, you just do t.test of the two vectors of smokers and non-smokers. Right? The smokers are going to weigh less, right, on average, than the non-smokers, so we're going to get the negative values again. Right? Partly I want to do these as negative values. It would be fine to switch it and do a confidence interval where things are positive, if that's easier to express as a difference. But however you do it, you have to explain it in context, right? Like, which one do you like to talk about more, chocolate or vanilla? So this 95% confidence, here the two averages get reported, and I edited this a little bit to make it fit on the handout. And so here's our 95% confidence interval. And so it goes negative 190, negative 191, up to about 28 grams. So it's not centered around 0, it's centered around the negative value, negative average difference. But it does include 0. All right, it doesn't quite exclude 0. So in a hypothesis testing world, we're not going to be able to say there's no difference. Maybe there's no difference. It's kind of tending toward there being a difference. But, right, one reason this might not be significant is there's only 90 in this group. Right? So divided by square root of 90 is not that big of a divisor to do it. The asymmetry of the groups really hurts in terms of testing, or the width of the interval in this case. Right. You could do it with equal variance, right? If you thought these two things were kind of equally spread. This one looks like it has a lot more spread, but that might be just because it has more than 10 times as many cases, right? You get 1,000 cases versus 90, and the one with 1,000 is likely to have more cases that are more than 3 standard deviations away. Right? So it's a little hard to tell. Kind of the central core here looks about equal width, and the kind of these things are, so the standard deviations between the groups might not be all that different. We could check, right, actually, right? We could do the standard deviation of the weights of the smokers and standard deviation of the weights of the non-smokers. There's a little bit difference, but that is not a factor of 2. I think it would be plausible to put them, consider it as equal variances. But the intervals do shift quite a bit, right? The one with equal variance ends up being kind of wider. You might try to think through why that might be, right? The variances are kind of equal, but the non-smokers is the much bigger group that has the bigger one, and so the pooled variance is going to be bigger, kind of maybe like 540, something like that. And then the driving force is at 90 sample size, right? So 40 over the square root of 90 is a lot different. Well, yeah, so 540 versus, so there's about a 10% difference, almost a 10% difference in that standard error related to that group, and that's going to be the dominant one in terms of width because of the small sample size. So the interval ends up being wider. This Welch t-test had to do with degrees of freedom, so it had that Welch complicated formula for degrees of freedom. It came out to 102.38. So instead of having, well over 1,000, 1,500 as the degrees of freedom, because that one group is so small, it's saying you need to use something like 102. So kind of a big price to pay to not have that. So it's only 102 gets used there. So that was one interval, the bootstrap percentiles. For this one, we have to bootstrap the smoker weights, and then we have to bootstrap the non-smoker weights, and what we record is the average difference of the new bootstrap samples. So one bootstrap sample, we have to do both independent groups. But besides that, it looks much like the other thing. So if we do that, set up our thing to hold the output, I'm going to record my sample sizes, so I don't have to. I kind of initially thought I would change this to 1, 2, 3. I forgot to change that, but it doesn't matter much. The bootstrap, here's what the average differences look like. The quantiles are those places there. The original average was there, and these, for this case, end up being quite symmetric. This is my little trick for trying to measure symmetry. And there's not much of a difference between the width here to the width here. It's quite similar. This one, these intervals are a little narrower than the t intervals. So there's kind of a caution about using bootstrap percentiles. It seems like a very fine idea, but they tend to produce intervals that kind of empirically look a little bit smaller. Anyway, that's one interval. The standard error version of it, right? We calculate the standard error. We're going to use the degrees of freedom from the Welch one from unequal variances, right? 198. The bootstrap, we didn't do anything to make it equal variances in any way, so we'll use unequal variances. And so it's that t-value plus or minus times the standard deviation of those boots. This one was very close to the t-distribution, 1. And there's this other interval, pretty close to the t-interval. And our bootstrap t-interval now, we're going to do it a certain number of times. We're going to restore those t-values we're going to simulate. We resample from the first group, resample from the second group, and then this is the thing we have to compute. It kind of goes over to that line, right? So we're going to have the x bars difference from our bootstrap samples minus the x-bar differences from our actual samples divided by an estimate of the variance from ours. Right? And this is the one from the unequal. So it looks a little bit more involved, right, to do that. We run all that. Those quantiles are there. The estimated t quantiles are about -2, and then 1.97. They're almost symmetric. They're not much different than the. No, that's just what I typed up there. The quantiles.
1.9.
This thing, yeah, was pretty similar. Right? -1.98. So it's shifted just a little bit from that. It's not making much of a difference, but it's just a little bit asymmetric. Right, and it kind of overplots because it's so close, you can't really tell the difference. So our interval is going to take the difference in the mean from our original data, the t-values from the bootstrap, and then an estimate of the variance of the difference from our original data. Now we get this. The interval is a little wider, particularly it's a little higher on top. It could be a little higher on top because this value is a little bit lower to the simulation, so it kind of makes an adjustment. And yeah, so given this sample, probably given a really small sample of current smokers, among mothers having babies, and just the big variability in their birth weights, it appears that there's no significant difference. But you suspect it's kind of trending towards that size. If you had 900 smokers or 10 times the sample size, you might think that it would be different, but you can't exactly prove it with these data. Right? You couldn't go to a court and say, look, the smoking has caused this, and then whose fault is that anyway? But so there'd be other legal issues, but you wouldn't really be convincing as a legal argument, because it could be, that's just the nature of statistics. So those are our different intervals, right? The book suggests the bootstrap t is very desirable. I think it makes a lot of sense to check the different ones and either report the ordinary t interval that people are familiar with or this bootstrap t. It's a little bit more work, right, to write that program to do it, but it's not too bad. So the person that came up with this international prize in statistics is an international prize in statistics. Prizes for a number of things, right? There's 5 leading international statistical organizations. The organization, I don't know if it listed. So American Statistical Association, International Biometric Society, Institute of Mathematics, International Statistical Institute, and the Royal Statistical Society out of England, right? Of course, that's not all. There's statistical associations in India and China and South Korea and just about every other country that are fairly substantial. But anyway, these got together and have a fund for a prize, all right? And nominations, previous winners. So the first winner was Sir David Cox, who came up with Cox proportional hazard model, so the development of survival analysis and other things come from him. And the second one was Bradley Efron, who's at Stanford. And so his work is in Bootstrap. There he is. He's been a professor at Stanford since the 60s, so still active, still traveling. So, but he's been a professor of statistics and also biostatistics at Stanford. Works on a lot of applications and developed the ideas of the bootstrap, the theory going behind it that people continue to study. And then many things in geometry of statistics and something called exponential families. So broader groupings of the statistical distributions and how they relate. So, and just the general impact through students who have done machine learning and other things is very high. So, in any case, so it's something that's fairly substantial, and computing now can handle it pretty readily, and at some point, students will learn. Well, we're learning how to program it. He has a book with some students that have a Bootstrap package, and so different parts of the Bootstrap package kind of automate this process. We're doing it sets of commands for doing it. So that's what we're going to essentially we have to talk about today. I suggest. Where is this? Oh, there it is. That's right. That was chapter 7.6 has is some additional discussion of properties of confidence intervals. Different aspects of their performance, coverage, etc. Kind of with the conclusion that there's still some work, possibly to be done. Can things be improved in terms of confidence intervals for different areas? Are there good ways to provide limitations to what can be done in terms of the bootstrap, in terms of sample size, skewness? And so it's still, it's for most of applied statistics, I think that there's really standard methods and then alternative methods for comparing those, but there'll still be future developments of things. And as the large data sets, really you fit bigger and bigger models, and things then start to be harder to tell what's the best. But underlying it are some of these properties of coverage and some of the techniques like simulating the sampling distribution, looking at pivots, get used in other ones. So that's what we're going to talk about in terms of chapter 7. I encourage you to look at that part kind of as a conclusion to that. This should be enough to do all the homework problems. And on Wednesday, we'll start revisiting hypothesis testing. Okay. Thank you.
Are we done?
Yep.
Thank you.
See you.